So thank you, Thomas. Thank you very much to Ubushi and the other organizers for inviting me here to what's been an extremely enjoyable and friendly conference and a very interesting conference for me. I think I'm losing the mic. Is that all right? It's working? That's okay. Okay. So I wanted to talk about some work in progress on the quantum reality problem. And I should start by saying, let's see. Yes, that's working. What I mean by the quantum reality problem. This is a sort of foundation super friendly audience, but still there are differences of terminology. So it used to be traditional for people to talk about the measurement problem. Sometimes we still do, especially if we're trying to talk to colleagues outside our field and trying to explain something about what we're doing. Sometimes when people talk about the measurement problem, they mean exactly what I mean when I'm talking about the reality problem or something very close to it, but not always. And I prefer the term reality problem or some synonym to that because we don't really want to focus on measurement itself when we're trying to understand what quantum theory is really about. For instance, focusing on measurement obscures the fundamental problem we're faced with in trying to make sense of a quantum theory of cosmology. That we start from a quantum state with no structure, and structure emerges apparently from within. Quasiclassical structures emerge, and eventually here we are. And at this point, we're able to talk about measurements, but we want to understand the whole process of the emergence that got us into this position in the first place. So what would count as success? What would count as solving the quantum reality problem? Well, it's a reasonable first ambition that I think I've outlined here, but also a pretty tough ambition. We'd like a mathematically precise solution. The whole point is to try to make quantum theory a mathematically precise theory in every respect, including its description of events. We'd like it to be Lorentz covariant, I think, most of us. And we'd like it to be talking about we'll get the hang of this in a minute. There we go. Some mathematically well-defined objects. John Bell's terminology, beables, or if you prefer, elements of physical reality. I don't think anybody is necessarily super committed to some particular mathematical structure. They could be events, they could be histories, they could be paths, they could be other mathematical objects. But we want to be able to talk about the sample space of configurations of these things, so the way that all the elements of reality could pan out, and then a list of all the ways in which that can happen, and a corresponding probability distribution on that sample space that applies maybe to every closed quantum system, but at least to physically relevant closed quantum systems, and in particular, in the end, to our universe. So if we had such a thing, we could tell a story about physical reality that still might be wrong, of course, but at least makes mathematically precise sense, which is that physical reality is exactly one of these configurations. Which one? Well, our theory doesn't tell us that. It just tells us there's a probability distribution. And it's randomly chosen from using that probability distribution from the sample space. If we have a story like that, well, in particular, it better imply quasiclassical physics in realistic models. And so we should be able to, in particular, derive Copenhagen quantum theory and classical dynamics as obviously very successful theories that work very well in their own domains. We should be able to understand their validity from this proposed solution. So the sort of story I have in mind that I've just outlined is a block universe picture. The theory is a list of configurations of beables, elements of reality, and probabilities. And I'm going to assume, if I can get away with it without further discussion, that it makes sense to talk about theories of this type. that it makes sense to consider fundamentally probabilistic theories of realist Bloch universes and configurations of beables in a given space-time. That isn't to deny that there are issues there. People worry about what fundamental probability can mean in this context. There are reasons, if you care about process in physics and the problem of the apparent emergence of time, there are reasons to worry about whether Bloch universes fit as well with that as one would like. So there's a discussion to be had on this, but I haven't got anything to add to that discussion today, so I will try and avoid it. And then we have obvious problems. Why would one try and do this, even assuming one's persuaded that quantum theory has problems that ought to be solved? How can we possibly hope to make progress when we don't understand quantum field theory, relativistic quantum field theory properly, even without the reality problem, and we're going to need a mathematically precise definition of relativistic quantum field theory to solve it? And if we're going to talk about cosmology, we need to understand quantum gravity. We don't understand quantum gravity. So it's, I guess the thrust of this objection is that even if this is a real problem and it's worth addressing, we're not in the right place. It's premature to think about addressing it. I think I would have to agree, at least with the force of the first of those. The best thing we're going to be able to do is give unrigorous formal definitions in quantum field theory because we don't have a rigorous formulation of quantum field theory. I would say, it would counter, though, that even with formal definitions, you can hope to replace fundamental conceptual problems, like the reality problem, by fundamental technical problems. How do you make sense of this particular formal quantity in quantum field theory? And that could turn out to be progress. It could turn out to be indeed the right way forward. As a more general comment, it's not obvious to me which of these three problems is prior. You could easily turn the argument the other way around. How could we possibly start thinking about quantum gravity when we don't even understand what quantum mechanics is really about? That's a less traditional way of thinking about things, but I think it's an equally valid point. So I don't want to dismiss these objections. They're important objections. But I don't think they should preclude us from trying to make progress on quantum reality as far as we can. Why do we want things to be mathematically precise anyway? Unification. The whole thrust of theoretical physics has been to try to find mathematical structures that incorporate more and more of what we understand in physics in a consistent way. This vision offers, in principle, a conceptually clear route to explaining all of physics from one fundamental set of postulates. That might not be an achievable goal. Even finding a unified theory in physics may not be an achievable goal. But I think most of us agree it's a goal worth striving. Why do we want our solutions to be consistent with standard quantum theory and relativity? Well, not out of dogma, but certainly because it's intellectually interesting. These are very interesting theories, and we'd like to know whether you can solve the quantum reality problem within them or whether you need to change quantum dynamics. And a second, more radical thought is once you have a solution, you're in a very good position for constructing generalizations of testable generalizations of quantum theory. And testable generalizations that may be different from those that are familiar to date. So the work I'm going to talk about today fits into a little research program in which the idea is to understand this story about beables and configurations of beables in terms of possible outcomes of fictitious measurements that take place far, far, asymptotically far in the future on a state that unitarily evolved from an initial state, psi 0, and that could have been very far in the past. So psi 0 lives on an initial hypersurface. There's some far future space-like hypersurface, S, and we want some story about fictitious measurements on S, and then we want to use those data, psi 0, and the measurements, and course, the Hamiltonian or the unitary evolution, to try and fill in a description of configurations of beables and measurement probabilities for what's actually going on between S and S0. All of these things, every time I talk about measurement, and I'm going to keep underlining it, I'm talking about a formal mathematical device. I'm not talking about us or anybody else actually going in and intervening in the universe with actual measuring devices. So, the idea is to take a finite time version of this, where S and S0 are separated by some finite time or proper time, and then take the limit so that S recedes to future infinity. And the hope, if the model is doing something useful for us, is that we have an asymptotically well-defined solution in this limit. So the probability distribution for beables, for the elements of reality, for our story about physics anyway here, becomes independent of S as S recedes to future infinity. Well, that's something you have to test out in any particular model. That's the hope. And it's that limiting configuration that defines our probability measure. And we're willing, you're not going to get anything for free. We don't want to make too many assumptions, but I'm willing to postulate a fundamental split of the Hilbert space into two different types of degrees of freedom that play slightly different roles. And the idea is this is just a law-like split that's given to us. And in particular models, we'll choose particular choices of HA and HB. All right, so the work I want to talk about now is exploring these ideas in which one of the Hilbert spaces is the electromagnetic field, and we're working in Minkowski space. And we start out with psi 0, the initial hypersurface on which the initial state, sorry, S0 is the initial hypersurface on which the initial state psi 0 is defined. Here's some final hypersurface S, and if we just unitarily evolve everything, we'd get a state psi. And we want to know something about what's happening at a point X or in a region around a point X between those two. And the idea I want to explore is that we can understand, we can at least write down equations that we could write down equations for elements of reality at X, so we can try and understand the physics at X, by the following sort of construction. First, you follow the forward light cone from X until it hits the future final hypersurface. Once it does that, you go along the hypersurface out to infinity in, I've only drawn 1 + 1 dimension, but obviously in every direction. So this is not quite space-like here, of course, it's light-like. So really, and I have a slide on this in a minute, really we should be talking about a limiting construction in which we have space-like hypersurfaces that are very close to this and tend to the light-like one. And if we had that, so let's pretend this is space-like for the moment, then psi here can be calculated directly from psi 0, the initial state, by our unitary evolution, which is evolving from one space-like hypersurface to another. Okay, so we can do that. If we're talking about measurements, well, that means we could calculate the joint probabilities of measurements along this bit of S prime, this green constructed surface, and this bit, and measurements at X. These are all at space-like separated points, here, here, and here. And we can calculate psi on this surface, modulate that limiting construction. So we can calculate a joint probability for sets of measurement outcomes at these various points. And to do that, we just need the unitary evolution law and the Born law. So as I said, we're really using limiting construction here. We're talking about measurements on S1 and then on S2 and so on. And hoping that as we take the limit, we end up with a well-defined result. And this construction was used for a different purpose, different purposes a while ago by myself and in a more closely related context by Daniel and other colleagues more recently. So what's the idea? Well, the idea is we're going to look at the measurement outcomes on the bits of the final hypersurface that we're allowed to, so here and here. There's going to be a list of measurement outcomes. They correspond to a way physics could have turned out, a configuration of beables, although we haven't yet defined the beables. In short, what I'm going to call a world. One of the possible worlds that our theory describes. Our theory describes a long list, an infinite list of possible worlds, and associates probabilities. At least that's the vision. So if we want to know what's the probability in that world of getting the measurement outcome little a for an observable A at the point X, well, we could just calculate it directly from the joint probabilities. The world's defined by having these outcomes on, so S intersect S prime is just these flat bits here and here. And we need to normalize by the probability of those. And again, it's interesting that this follows directly from standard quantum theory and the Born rule. Although there's something about future and past going on here, there's no need for postulates about post-selection or to use the ABL formalism in this particular context. Nothing against the formalism, but it's interesting it doesn't arise here. So now if we make specific choices of measurements that are supposed to be the right things to look at on S, and we make specific choices of the things that are supposed to define the beables at A, at X, specific choices at A that define the beables at X, we have a construction for defining elements of reality at X. So this is important. We want this, we want to think about measurements on the final hypersurface one time only, and we want to use that same set of outcomes to define the beables everywhere in space and time. So if I'm defining beables at X, I only use the outcomes here and here, so I only use a subset of all the outcomes. But if I was thinking about the beables Y, I'd have the same list of outcomes, and I'd use a different subset. So if Y is here, my subset would start there and continue that way, and it would go off that way. So just one set of measurement outcomes on S. For every point X, we use a different subset of those outcomes in this construction. We want the story to end up being asymptotically independent of the final hypersurface S. Given our light cone construction, a natural way of doing that is to think about observables on things that travel at light speed. So that if stuff is radiating away here, it's at least got a chance of continuing to radiate outside the light cone and show up in the measurement. If we're talking about a fundamental split in nature, you could argue that perhaps the most natural fundamental choice would be between matter and gravity. But it's not the only reasonably natural choice. Bosons and fermions would be another, massive and massless particles would be another. And for the moment, I just want to focus on photons versus the rest. So let's take photons as our choice. At least we could do some physically relevant calculations in toy models with photons. And the idea is going to be now that the real physics, the beables at X, are determined by the initial state and by observables of the electromagnetic field, that bit of the electromagnetic field that is radiated away outside the future light cone of X. towards future infinity. Okay, well, let me give you the crudest and simplest toy models, because it captures a little bit of the intuition in a way that may be helpful. So space-time is 1 plus 1D, fine. My photons are a bit of an embarrassment. My photons are, I'm going to model by point-like objects that just travel on one left or right along light rays. And if they hit massive objects that reflect, then they just bounce the other way. So it comes in and goes out. We're not going to worry about the fact that that should give the object a kick. We're going to neglect the moment of transfer. Nor are we going to worry about the fact that the object has a wave function which has a finite spread, and that spread will change over time. We're trying to keep everything as simple as possible just to get some idea of the picture. So the object is going to start in a superposition of two position states. This one on the left and this one on the right. So space is going this way. This is supposed to be a representation of the superposition. Time's going up. And we want to know, following these sort of simple-minded rules, what we could observe about the photon field outside the future light cone of any given point. We're going to assume the environment has just two photons in it, one coming in from the left that may or may not hit the object here. It's in superposition, so we're uncertain. And one coming in from the right. Similarly, could hit the object here. Could hit the object here. So if you look at an early point, x0, t0, look at its light cone, which goes there and there. Well, whatever component of the superposition we look at, the photons are going to bounce. So for instance, this photon is either going to bounce up here, which is inside the light cone, or if we look at the component that corresponds to the other part of the superposition, it's going to come in and bounce up here, even further inside the future light cone. So there's no information outside the future light cone. If we think of a measurement as just a click where the photon hits the measuring device, well, we're going to get no clicks there, no clicks there. There's nothing to infer. And so if we look at the expectation value of, say, the mass density, it's just the expectation value in superposition. Our beables are telling us that we have an uncollapsed superposition at the level of beables. Here, we have a cloud of mass density and another cloud here. And the weightings depend on the coefficients of the superposition. On the other hand, after the photons have had a chance to interact, if we look, say, here, and now look at what's outside the future light cone, well, you will get a click from a photon here in this component. Alternatively, you'd get a click from a photon here in the other component. And you can tell the difference between those two clicks. So what you'll actually see is a click here and here, or the symmetric alternative, which would be a click here and here. All four of those possible click locations are now outside the future light cone. So you have complete information when you do your calculation. And if you get this and this, and ask what's the expectation value of the mass distribution, given that and that observation and our rules, it tells you that all the mass is here and none of it's here. If you had the other alternatives, it would tell you it's all here and none of it's here. So in our toy model, we're getting a collapse at the level of the beables as a result of these interactions or potential interactions with incoming photons that bounce off the object and radiate away. Start out superposed, end up collapsed at the level of the beables. The quantum state, of course, we haven't said anything new or different about it, just evolves unitarily. Okay, well, that is a I hope that's sort of helpful in beginning to get some intuition, but it is a very simple-minded and unrealistic model. We can do at least slightly better. We can look at physical systems that absorb or emit a number of photons using multi-photon wave mechanics. To do that, I'm going to need some story about how we measure the photons at the final time, some model of photon measurement in position space. The story I'm going to use is a bit of a placeholder. So I'm going to use the formalism for photon wave functions that was developed by Saib, Bialynicki, Birula, and pronunciation, Smith and Raymer, and others. There's a long, interesting, and to my mind, sort of unresolved literature on the status of photon wave functions. I don't want to make any new claims about this. I'm simply using them as a tool in toy model. And I'm going to introduce the idea of a fictitious photon position measurement that's just given by using, in a simple-minded way, the position space Born rule for the photon wave function. So you have a photon wave function, gamma xt, and you carry out a measurement at time t. The rule is going to say the probability of getting a click, but x is just given by mod gamma squared. I am not saying that that's the right thing to do, fundamentally. We don't, as far as I'm aware, have a really satisfactory fundamental treatment of photon measurements in photodetectors, when we're talking about full relativistic QED. And this is no more than a placeholder pending such a fully satisfactory treatment. In its limited defense, it does give physically sensible answers in the particular context in which I'm going to use it. But you could certainly use other ways of extracting measurement-like information from QED. For instance, you could actually imagine an array of photodetectors along your hypersurface and use standard models of photodetectors. Or you could perhaps use models from the ideas from the collapse model literature, such as Philip Pearl's recent non-relativistic model of photon collapse, but applying these only after the final hypersurface X, so that we're only using them to extract measurement information. Or other ideas about relativistic collapse models, but again applied only after. Okay, what we're going to do is not that, it's our simple-minded photon wave function model. So we're going to assume that there's some finite number of photons that have been emitted or always there in our system. They're going to radiate around, interact, and on our late-time hypersurface, applying the multi-photon wave function Born rule, we're going to get a set of clicks. 1, 2, in this case, n clicks. And remember, if you want to understand what happens at a position x, if you want to understand the beables at x, then you want to look at the measurements outside its light cone. So some subset of the clicks, in this case, these and these, are going to be the ones used in the calculation for the beables at x. Okay, well now we can at least look at things that look a little more like physics. So here's a simple model of two-level emission, and an atom starts in level 2, it emits a photon goes down to level 1, emits a second photon, goes down to the ground state. We can model this in photon wave mechanics, write down expressions at least in a particular frame for the photon wave functions that result from a process like this. We can model it. And we find that the probability of detecting a single photon that's a radial distance this big or more from the atom at a late time t is given by some familiar expression, 1 minus e to the minus gamma 1t. And the probability of detecting a second photon closer than the first one, so R2 is 1, is given by a similar expression with gamma 2 and R2 minus R1. And both of those are independent of our late time, big T. So at least in this model, we have success in the form of expressions that are asymptotically well-defined. If our beable is the energy of the atom, the model tells us that there is a definite transition in the beables from level 2 to level 1 at some time. The time will be random, but it will be of the order of gamma 1 to the minus 1. And each time we run the model, it will be a different time. And then a second transition, so that the atom energy beables go to the ground state within a few multiples of gamma 2 to the minus 1. On average, within gamma 2 to the minus 1. Those times are randomly determined by the detections of photons on the final hypersurface. If you want to think of a macroscopic collapse, well, here's a simple model. So imagine a sphere with a little hole, and the reason I have the hole is I want to put an excited atom into the sphere. There it is. But we're in superposition. So the sphere, we have the sphere with the hole here, it's superposition with the sphere in the hole here. Without disturbing anything, I'm going to introduce the atom here. So it's close to this part of the superposition, but far away from that one. And the atom's in an excited state, so that we expect it to emit a photon. And we're going to assume that the sphere is a perfect absorber. So the component that is over here, the photon will be emitted and straight away absorbed, and I'm going to forget the annoying possibility that it might go out through the hole. Let's assume that it doesn't. So over here, we get absorption. If the thing's over here, well, it's going to radiate away to infinity. And I'm also going to neglect the small possibility that even though it's over here, the photon might radiate in this direction and be absorbed anyway when it hits this thing. There's no fundamental problem in allowing for the hole and allowing for that second thing. They just give you extra small terms that make perfect sense, but slightly clutter the story. So we start at time 0 with the state of the sphere in a superposition and the atom in an excited state E. At late times, we expect the superposition now to be some, so to speak, excited state of the sphere. The sphere's absorbed a photon, it has slightly higher energy, together with the ground state of the atom, or the other component, sphere as it was, atom in a ground state, and a photon radiating off towards infinity. So photon wave functions propagate causally. This is the reason why they're good in these models. And we can work out the probability of a late time detection. Again, we find that these probabilities are asymptotically independent of time t. And again, our postulates tell us that there'll be a definite transition from the superposition to one component or the other at a definite time. The time will be determined randomly by the final measurement outcome of the photon, if there is one. And these are the resulting states. And the respective probabilities, of course, the Borel probabilities. How am I doing? Okay. So if we try and even intuitively go beyond toy models, are we pressing with intuitions that make some sort of physically reasonable sense? Is our intuition about the asymptotic behavior of the electromagnetic field a reasonable one? Well, I would say it's at least consistent with some standard ideas about what's going on in cosmology. That interactions become sparser and sparser as the universe expands forever. That in the late universe, photons will propagate essentially freely, pretty much forever. So ideas along the lines of the big rip or the big freeze scenarios. they're also, as far as they go, consistent with the intuition that the right way to understand quantum field theory is in terms of asymptotic scattering amplitudes. That's what we're trying to do here. We're trying to get some sort of story in which very, very late time, asymptotically late time, data is extracted from the field, and we use that to construct what's going on. Certainly the case that there are other cosmological scenarios in which it's harder to justify, maybe not possible to justify, the intuition that the photon, the electromagnetic field, carries away records of macroscopic, quasiclassical macroscopic events, which persist to the end of time. So there's something cosmologically contingent about this set of ideas. Maybe since we're uncertain about quantum gravity and we're uncertain about cosmology, maybe one should be happy enough with this state of affairs. They're consistent with the ideas are sort of consistent with mainstream scenarios, and we just can't say for certain how things are eventually going to work out. Do we get physically sensible pictures of quasiclassical physics in the beables? Well, in the toy models, yes, we definitely do. More generally, I believe the answer should be yes if two things hold. And the first, I think, is pretty uncontroversial, that photons scattering quickly decoherence macroscopic position superpositions. There's a long literature on this going back to the pioneering work of Yosin Zhe, and everybody agrees that photon scattering is phenomenally efficient in decohering position superpositions. The second intuition, the second thing we need is that if you have a macroscopic superposition sitting here in your lab and photons come in and are scattered, that some of them actually make their way through the building or produce something in the electromagnetic field that makes its way through the building and does eventually propagate off towards future infinity. So there may be some delay here, there may be scatterings and rescatterings, absorptions and re-emissions. But a record of quasi-classical stuff sitting in your lab makes its way off towards future infinity, eventually with little or no scattering and absorption, and so no re-emission and rescattering. Well, my intuition at least is with some delay, we should also strongly expect that. Asymptotically, so what happens at very, very late times, well, the answer depends on cosmology. It depends on the ultimate fate of the universe. And we just, again, have to accept that there's something cosmologically contingent about this line of thought. Some worries. We would need to be able to handle infrared divergences, this annoying issue that the photon number is unbounded, and we would need to think about potentially measurements of arbitrarily large numbers of arbitrarily low energy photons to give a full quantum field theoretic treatment. And of course, we need really something better than the photon wave function measurement model I've given. We need a fully satisfactory treatment of measurements of asymptotic electromagnetic field states in QED. An optimistic gloss on this is that what we've done, or what we're in the process of doing, is replacing the quantum reality problem by another problem that's perhaps a more tractable problem, and is anyway a problem that is already with us. So at least we replace two problems by one. I think, as I said at the start, replacing fundamental conceptual problems by fundamental technical problems perhaps is progress. One can hope. What sort of picture of the world emerges if these ideas are on the right lines? Probabilistic realist block universe picture. We have one probability distribution, which is determined by the Born rule on the late time measurements. That defines the configuration of beables, and so the quasi-classical events throughout space-time. The final time measurement, that's just a mathematical device. We don't need to think that dice, so to speak, are actually rolled at the end of time, and then this retrocausally determine things. Just need a couple of minutes. If you want to talk about a dice metaphor at all, it's perhaps better to say the dice are rolled outside of space-time, and then they select a space-time and everything that's happening within it. In any case, our beable descriptions of quantum subsystems can only really be properly understood as part of an irreducible whole. You need to solve everything in order to understand everything in this picture. So the state vector for an individual system defines a probability distribution of the beables. But to understand the correlation among these probability distributions, we need to understand the full future evolution of the universe. So for instance, in a Bell experiment or a Pusey-Barrett-Rudolph experiment, if you just look at the beables at times up to the experiment, they don't explain why you're going to get the correlations you're going to get. You need to understand the data that's obtained from the late time measurements. So the beables don't necessarily distinguish the states, but nor do they determine the joint measurement outcomes. This isn't a epistemic model, nor is it a psiontic model. And one last comment. I promised a route to generalizing quantum theory. There's a very simple point, but it's perhaps still underappreciated. Once you have a theory about beables, whether it's de Broglie-Bohm or collapse models with flash ontology or this sort of story, you have a path to generalizing quantum theory in enormous numbers of ways. You have a probability distribution on beable configurations. The beable configurations describe reality. And you could reweight that probability distribution and then renormalize by any weight function you like. And these give you modifications of quantum theory. You call them beable-guided versions of quantum theory. And you can think of these as foils. So we believe in standard quantum theory, and we want to use these to parameterize how well we've verified standard quantum theory. But if WC is simple enough, if you have some good reason to take a particular weight as a genuine candidate for theory, they're also potentially genuine competitive theories to standard quantum theory. So you can imagine cosmological models in which cosmological expansion is enforced, at least partly, through a beable weighting. Okay, there are other things I could say, but I'm running out of time. So thanks very much for your attention. I'll stop here.
Did you take a special choice for these observables A at the point X, or maybe?
In the toy models, I was mostly looking at energy, but I guess a natural choice would be T mu nu of X.
The energy.
Another possible interesting choice would be current J mu of X.
Or position, or?
Sorry?
Or position?
Position, well, position of
the particle?
Yeah.
Position operator?
I guess, I mean, we want to talk, the aim in the end is to have a model that works, that is Lorentz covariant and works for field theory. So to me, J mu nu, or, sorry, T mu, J mu would be the most natural choices. But you're free to look at other stuff. Well, there's only one measurement of T mu nu involved at the point X. Oh, one at a time. So you get it. You do a calculation for T naught naught, and then another one for T naught 1, and so on.
Yeah. Sorry, I couldn't understand. You want to your main aim is to have the measurement in S intersection of S dash, right?
Yeah.
Yes.
I've lost the picture, I think.
Yeah. So that is your main aim. But the future light cone, the part that comes under the future light cone, is S minus S dash, right?
I'm not sure if we have our conventions right. S minus
S in the future light cone of say you have a beable at X.
Yep.
And the future light cone of that X in the final the final time at S.
Yeah.
So that comes, S dash comes outside of that, right?
So the measurement outcomes you take account of are the bits outside that, exactly.
Yeah.
Yes.
Yeah, so how would you get the measurement at S intersection S dash? Because it's outside the future light cone?
So the measurement is the postulate is that a fictitious measurement is carried out everywhere along that thing. And that defines data which we use to construct the beables. Is your question, how do you actually signal these things? Well, you don't. Nobody's carrying out the measurements, nobody's sending signals. It's data that you use to construct what the beables would look like in one particular world. If you want to understand, if you want to make a prediction, well, then you have, in principle at least, you have to do that calculation for every world, and then look at the data we have and see which worlds are consistent with that, and then calculate the expectation values within that.
There was one more question there, correct? Then we shall finish because we are running out of time.
Sorry, it's a little vague, which is why I hesitated to ask it right now. But it seems like this framework, shifting the final hypersurface to infinity, to asymptotic, is a good way to recover covariant observables. That's the theory that you're looking for the entire evolution. So there's a lot of similarity to what we do in ordinary field theory, which is sort of the S matrix kind of.
Yes.
So I think I understand that part, but I still am trying to understand where the realism is. I didn't quite catch. Where is realism hiding in here? Because it looks to me, some way of looking at it looks just like how we do S matrix scattering. And
where is the realism hiding? Maybe this, we calculate real quantities at points between the initial and final hypersurface. That's where the realism is. Maybe this is helpful then. At an intuitive level, what we're doing is you want to know whether your macroscopic superposition collapsed this way or that way. What we're doing is noticing that photons are coming in and bouncing off it, and you get a different pattern of photons, whether it was this component or that component. And those photons, some of them at least, will continue to make a record that propagates outside the future light cone of this point forever. And we're reconstructing, through the mathematics, from that record, the answer. It was here, or it was here. The record's consistent with one of them or the other, but not both. I don't know if that's helpful, but I'm certainly happy to try and say more offline.
Okay, let's thank the speaker again. Thank you.